All right. So you all should have watched a video before you came today. And again, we're going to work on the assumption that, like, in my heart, I'm going to believe that you all watched the video, but in my head, I'm going to know it's not true. So I'm going to give a quick, like, 3-slide, like, review of stuff you should know. And if you don't know, you should feel bad. And then we'll go on to the stuff that we're going to do today. So, with that said, name that. So, how many carbons do we have? 7. So, that's going to be hept. But we have a double bond in the molecule. So, it's not heptane, it's heptene, right? Because ene is the suffix for a double bond. And then, what carbon does our double bond start on? Got a number this way. So 1, 2, yep. So it's going to be 3 heptene, right? The rule of thumb is that you only put the number that the double bond starts on, because the assumption is that if it starts on carbon 3, it goes to carbon 4. So you just have to put the first number, because then that tells you, you know, which direction it's going and everything. Now, we have to be able to differentiate the stereochemistry of this double bond from other double bonds. So is this double bond cis, trans, E, or Z? So many options. So we can say that it's going to be either cis or trans, because on each vinyl carbon of the double bond, there's a hydrogen, right? So we use cis and trans when there's a hydrogen on each vinyl carbon of the double bond. And those hydrogens are on opposite sides of the double bond. They are across from one another, so they are trans. This is trans hept3ene. What would this be? How many carbons? 4. So that's bute. And there's a double bond. So that is ene. Double bond is on carbon 2. Doesn't matter which way we count, right? It's symmetrical. So bute 2ene. Is that double bond cis, trans, E, or Z? Cis. The 2 hydrogens are on the same side, so it's cis. This is cis bute 2ene. Eight. Octene, yep. So we're going to be 3. So we're going to number it this way. And we're going to have a bromine, so bromo, and methyl. So what are my other numbers that I need to have in here? Yep, 4 and 3. Ah, see. Now, we only use cis and trans when our when we have a vinyl hydrogen on each carbon. So there has to be a hydrogen on each carbon of the double bond. When you don't have a hydrogen on each carbon of the double bond, we use E and Z. So E and Z, you kind of assign similarly to R and S. So to assign E and Z, you break your double bond in half, and you look at one of the two carbons. And you assign priority to the two groups on that carbon. So on the blue carbon, what group has priority? The ethyl or the methyl? Ethyl. On the red carbon, which group has priority? The bromine or the carbon chain? Bromine. So your two high priority groups are on the same side. So this double bond is Z. So this is, we're going to pretend it's out front. Z, 4-bromo, 3-methyl, oct3ene. Right, so when the two high priority groups are on the same side, it's Z. When they're on opposite sides, it's E. And you use E and Z when you don't have hydrogens on each of your vinyl carbons. Seem good? Okay, so this is like a quick review of some of the stuff you should like take away from the video that I asked you to watch, or that you will watch in the future, because you're like, oh man, I don't know what he's talking about, right? But I want to get into the good stuff now. I want to get into organic reactions. Right? And you can break organic reactions kind of down to one simple rule. Atoms or molecules with electrons react with atoms or electrons that lack electrons. Right? This is a long way of saying a positive thing and a negative thing are attracted to each other. Make that an actual K. Atoms or molecules, sorry. Right. So you have to find your thing that has too many electrons, and you need to find your thing that is lacking electrons, and they're going to come together. Right? So that's going to cover 95% of the reactions that you're going to do. It's going to be a thing that has electrons and a thing that doesn't have electrons. So, right? Oops. And that's basically it. Positive things are attracted to negative things. Now, of course, we have to science that up a little bit. We can't just be like, oh, the positive thing and the negative thing, blah, 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 right? So, electron rich atoms / molecules are called nucleophiles. So things that have electrons, have extra electrons, are called nucleophiles. Now, please do better than the first section. What is in the nucleus of an atom? Protons and neutrons? Okay, awesome. They said DNA, and I wanted to die. Protons and neutrons. protons have a positive charge, right? So nucleophiles means something that likes the nucleus, something that's attracted to the nucleus. And the reason it's attracted to the nucleus is because the nucleus is positive, right? So things that have electrons want to react with things that don't have electrons. So electron-rich things are nucleophiles because they're attracted to the positive charge of the nucleus, right? These will donate electrons, right? So electron-rich atoms will give electrons to something that is lacking electrons. Uh-oh. Right, and then we have electron-poor atoms or molecules. Give everyone a second here. These are called electrophiles, right? They're lacking electrons. They want electrons. They love electrons. They need to get electrons, right? Because the electrons are negatively charged, right? So these things, electron-poor things, are positive. They want to react with negatively charged electrons, so they're electrophiles. These will accept electrons. So nucleophiles will donate electrons. Electrophiles will take those electrons. So we have our nucleophile, which is usually abbreviated NU. Our electrophile. Our nucleophile is going to give electrons to our electrophile and allow us to make something new. See what I did there? That's A+. Right? So that's most of our reactions, right? Is find the thing that has electrons, make it give those electrons to the thing that doesn't have electrons. For our first few reactions that we're going to be doing, right? The pi bond in a double bond is going to be a nucleophile, right? If you think about a double bond, right, you only need 2 electrons to hold 2 carbons together, right? To make a bond, you have to have 2 electrons shared. When you have a double bond, you have 4 electrons between 2 carbons. You have more electrons there than you need. So you've got a spot that has too many electrons, so it can go give those electrons to something that needs them more than those 2 carbons do. And so our double bond is our nucleophile, the thing that's going to add to something. Right? So I want to talk about organic mechanisms next, reaction mechanisms. But I got to give you a reaction first. Oops. So organic reaction mechanisms, this is showing how the electrons move during the reaction to make and break new bonds. So I need to give you a reaction that we can use to like write out a mechanism. So I'm going to give you hydrogen halogenation. Where we have a double bond and we add HX, so G, right? And X is a halogen. So we are going to add a hydrogen to one side of the double bond and a halogen to the other. So hydro for hydrogen, halogen for halogen. So you're going to add X to one side, H to the other. So I'm going to be a little more specific. I'm going to give you the reaction of HBr with our 2-butene. Right, let me get this. So the mechanism shows us how these things go together, how the electrons move to make this happen. So we're going to take this. So we know that our double bond is our nucleophile, right? It's the thing that has extra electrons. So we have to find the positive thing for that nucleophile to react with. So if we look at HBr, bromine is more electronegative than hydrogen, right? So when you're more electronegative, you pull electrons towards yourself. There's an unequal sharing of electrons in that hydrogen-bromine bond. So bromine, so this is a delta, which means partial. So the bromine is partially negative. It's slightly negative. And the hydrogen is going to be slightly positive, right? That hydrogen is positive enough that we can have the electrons from the double bond attack that hydrogen. Now, how many bonds can a hydrogen have? I didn't hear it. 1. That means when these electrons from the pi bond attack the hydrogen has to give up its bond to bromine. Hydrogen's a good guy, doesn't cheat, one bond at a time. So he's like, hey, bromine, you got to take these electrons and go. Right? So when the electrons from the pi bond add to the hydrogen pushes the electrons it's sharing with the bromine and onto the bromine. It just gives it all the electrons. So what this ends up doing is I make a new carbon-hydrogen bond, plus I make Br minus. Now, the electrons, I'll make them green. The electrons, the 2 electrons in that bond are the 2 electrons that end up in this carbon-hydrogen bond, right? This carbon here that is orange, it had electrons leave it, right? Electrons just left. It used to be sharing a sigma bond and a pi bond with the carbon, with this carbon. We'll make it green, right? But then those electrons left the orange carbon. So the orange carbon, because electrons left it, gets a positive charge. Right, so it was sharing those green electrons with the green carbon. Those green electrons got given to the hydrogen. So that carbon gets a positive charge. And the bromine, because it got 2 electrons from the hydrogen, when the hydrogen gave it its electron, it gets a negative charge. Now this part's really easy. I got a thing that is positive and a thing that is negative. They're going to stick together because negative things react with positive things. So I'm going to take this Br minus, and I'm going to have it attack the positively charged carbon, which is this orange guy right here. And that is going to make our product. So something I want to note, arrows start at electrons and go to atoms. Right. So you always start your arrow at electrons. So you start them at a bond. You start them at a negative charge. You start them at a lone pair. And they go to some place that is lacking electrons. Right? So you're always going to start your arrow like at this pi bond, and it goes to the hydrogen that is lacking electrons. So you're always showing your electrons moving to somewhere, moving to an atom. So we have all of these structures and all of these compounds that are part of this mechanism. We can kind of make a little more sense of them by kind of plotting their energies. And we do that on a reaction coordinate diagram. So reaction coordinate diagram is going to plot the energy of compounds in the mechanism on a graph. And this graph gives us insights into the rate of the reaction and the energetics of the reaction, right? So there are a few things that you're going to see on a reaction coordinate diagram that I want to kind of define before I show them to you. So it's not an I, it was just me not being able to write. I'm going to make starting material, just abbreviated SM, like all the time. Right, so you have intermediates. So intermediates are long-lived structures that are on the way to products. We make them, we can observe them, right? But we can't isolate them. So you have an intermediate, you know it's there, you might be able to see the color that it generates. You might be able to use spectroscopy and observe that that compound is there, but you can't like take it out of the reaction and put it in a bottle, right? It hangs around for a while, but not long enough for you to like keep and isolate, right? But these are things that we actually know are there that we can make measurements on. And the other things are called transition states. Transition states are structures between starting materials and intermediates / starting materials and products. They are short-lived. High energy, They're not observed. They always have partial bonds. Okay. So transition states will have half-form bonds. Right? So let's draw the reaction coordinate diagram for this first reaction that we have here. You have a reaction coordinate diagram. The y-axis is energy. The x-axis is reaction progress. Let's say this now. Higher energy, look at that space. Equals less stable. So the further up you are on the y-axis, the less stable that compound is. Right, so we have our reaction. See if I can get it all to fit in here. Right, we add to our hydrogen, push electrons over. We get our product. Erase these random dots. Right, so this is our reaction. We're going to draw the reaction coordinate diagram for. We have our starting materials, let's say here. We have our product, which we're going to just make PDT down here. It's our product. So the valley between the two peaks, this is an intermediate. Right. So it's not a product, but it sits in a valley, so it hangs out for a while. Right. In this reaction, our intermediate is, let me move that over a little bit, is that positively charged carbon. We can observe it, but we can't actually isolate it. The peaks are our transition states, which I'm going to just call TS for sake of being able to get everything to fit. So the TS, the transition state, is always the top of the hill, right? It is the least stable. These are the least stable parts of your reaction. Now, for this first step, where we add the HBr, the transition state, so I can get it to fit, is this. So dotted bonds mean partial bonds. So what this is showing is that I'm starting to break the carbon-carbon double bond. I'm starting to form the carbon-hydrogen single bond, and I'm starting to break the hydrogen-bromine single bond. So I have these dotted bonds. So I have these partially formed bonds. Now, we can't see transition states, but they make sense, right? They're the thing that has to be between the two things we can see. I'm going to unplug my computer, because if I do this and I don't, I'm going to rip my computer down. We'll start with the in-class people. All right, in-class people. Humor me. Close your eyes. Open your eyes. I went from one side of the screen to the other. Did I just poof and come over here? No, right? Even though you didn't see me walk across, you're not like 3 months old. You have object permanence. You know that I had to walk across. You know there was a transition from one side to the other. You know that at some point I was right here in the middle, right? Same thing for a molecule. The pi electrons don't just magically jump from the double bond to that hydrogen and knock the bromine off, right? It's a process. And if we can't see the process, we're smart enough to know the process has to happen. right? So you're not just like, oh, you're a wizard, Wakefield, right? No. You're like, oh no, I'm smart enough to know that he had to walk across. Zoom people. Ready? I'm on this side of your screen. I'm on the other side of your screen. I transitioned, right? Even if you didn't see me, that's a really bad jump. Ready? Close your eyes. Oh, yeah, see I'm on the other side of the screen now. Even though you didn't see me, you know I had to come across. You know I had to transition from one side to the other. That is your transition state. That is the thing that we can't see, but we know it has to be there. I think I used to like do the triple jump. Badly, mind you, but I did it. Right. So the transition state for the second step is where that bromine starts to interact with that positively charged carbon. Right. So if you think about bonds, there's a certain bond length, right? A certain distance that the atoms are apart from each other. And so that bromine has to get closer and closer to that carbon till it gets to that right bond length, and then they kind of snap together and make a bond. That's the transition state, is that bromine getting closer and closer and closer, and them getting attracted to each other and then snapping together and making a bond. Right? So those are our transition states. We can't see them, but we know they have to be there for stuff to make sense physically. Because even though atoms are small, they still are physical things that have to move and have to come together. And, you know, the bonds have to break. They don't just like magically go away, right? There's a process. And the transition state is representing that process. So we can get information from a reaction coordinate diagram, even if we don't know what the reaction that we're doing is. Right? So one thing that's really easy to pull out of a reaction coordinate diagram is the number of transition states equals the number of steps in the reaction. So even if you don't know what the reaction is that you're doing, you can count the number of transition states and know how many steps there are in that mechanism. Actually, reaction mechanism. In the reaction that we did, right, there are two steps. There's the adding the double bond to the hydrogen and then adding the bromine to the positively charged carbon. There are two steps. There are two transition states, right? Now, if you had a reaction coordinate diagram where you don't know the reaction, you can figure out how many steps there are in that reaction based on how many transition states there are, how many peaks there are all along the way to the product. So how many steps are in this reaction? There are three transition states. There are three peaks on your way to the product. So this are going to be three steps because there are three transition states. The valleys are intermediate, so they don't count for this. Just count the transition states, count the tops. How many steps are here? One. Super easy. There's one step because there's one transition state. So even if you don't know the reaction, you can look at a transition state, or you can look at a reaction coordinate diagram, predict how many steps there are. Another thing you can do from your reaction coordinate diagram is you can figure out if your reaction gives off energy or takes in energy. So in Gen Chem, you will write about exothermic reactions and endothermic reactions, right? Things that gave off heat or things that took in heat and got cold. Sadly, in organic, we decided to rename them, but they're basically the same thing. So there are two types of reactions based on energy. There are exergonic reactions and these give off energy, right? These are akin to exothermic reactions, but we're not just worried about heat, we're worried about all forms of energy given off. At the start of organic 2, you're going to make luminol, right? The energy that's given off when luminol reacts with iron is in the form of light. It's still an exergonic reaction. It's still giving off energy, but it's not giving off heat, right? And then there are endergonic reactions. And these are reactions that require energy to go into them to make them work. So you've got to put some energy in to make the reaction work. So endergonic. So how can we determine exergonic and endergonic from a reaction coordinate diagram? So in an exergonic reaction, your starting material is higher in energy than your product. Your product is energetically downhill, right? You can think about it, if you had a ball and you let it go, it would follow the blue arrow down and it would have more energy at the bottom than it did at the top, roughly speaking, minor in physics, whatever. If you have an endergonic reaction, starting material is lower in energy than the product. So here, you have to put energy into the reaction to push your molecules up to the energy of the product, right? They just won't, they just don't get there on their own. You have to give them energy to get them up to the energy of the product. So again, starting material. Right, so we're going uphill. Now, if any of you have taken Physics 1, you may remember the concept of work, right? And that work is a state function. It doesn't matter what you did, you're just comparing the two points at the beginning and the end. That's the same thing with chemistry reactions, exergonic or endergonic. It doesn't matter how many steps, it doesn't matter how many transition states, it doesn't matter any of that stuff in between. All you're looking at is the ends, right? So you can have a reaction right? All you're looking at is my starting material higher in energy than my product, or is my product higher energy than my starting material? What happens in the middle doesn't matter. All you have to do is look at the two ends, and that's what matters. So this reaction would be exergonic. All right. How many steps is this reaction? 2 steps, because there are 2 transition states. So I've got a transition state here and here. So the reaction is 2 steps. I have the intermediate is here. And is the reaction exergonic or endergonic? Am I going uphill to my product or downhill? Endergonic. So I'm going uphill. So this is an endergonic reaction. So I'm going to address this thing before I go on. I'm going to end here in a sec. But this question came up in the early section, and I just want to go over it real quick. It's a little out of place, but it'll work. So someone asked me, right, if I give you a reaction, do you have to draw the mechanism every single time? And there are 2 types of questions I'm going to ask you. I'm going to ask you questions that look like this, where I'm like, here's the starting material for the reaction. Here's the reagent. It is your job to tell me what the product is. And you're like, oh, I know the product for this one. It is this. Cool. Now, the follow-up is, eventually, I'm going to teach you rules. And so I'm never going to just give you a structure, on purpose at least, that was from your notes. Right? So your job is not to memorize all the structures and all the examples we do in class. It's to use those structures and examples to help you understand the rules so that I can give you any molecule in the world and you can look at it and go like, there's a double bond. I know that double bonds react with HBr to make this kind of product, and you can draw that product for anything, right? Because you know all the rules that let you predict what the product's going to be, right? So there's going to be those kind of problems. And then there's going to be problems that I will give you the starting material, the reagent, and the product, and I'll just be like, yo, what's the mechanism? And you have to draw the mechanism. Now, fake semester, usually it would just be this and then a blank piece of paper, and you would have to draw the mechanism. I've got to get creative with how to do this. I think for Organic 2 last semester, I broke the mechanisms up into steps, and then I was like, put these steps in order, right? I could probably do something very similar this time where I'm like, put these steps in order, or I could like have a bunch of little blank boxes that you have to draw arrows to and stuff. I'm going to come up with something. But like those are the 2 types of problems. So don't think that like you're going to look at a page and there's going to be 10 reactions and you have to draw 10 mechanisms. There's usually 1, maybe 2 mechanisms per test. But then I think for this first test, you're probably going to know 10 to 15 reactions. And I try to get all 10 or 15 reactions on the test in some way, shape, or form. So there's usually 1 big mechanism and then a bunch of like, here's what you start with, here's the reagent, apply the rules to this, tell me what you make. So just to give you a little heads up of like what's going to come, because I'm sure someone was like, I have to draw these mechanisms every single time. No, it's not that bad. And with that, if there are no questions, we're going to get out of here.